Hey everyone. We're gonna start something a little new this week. We're gonna start limits, which is the first part of calculus. This is a foundation that you're going to need in order to get through calculus, because pretty much everything is built from limits. We've talked a little bit about limits before, but not really what the foundation of limits are. The most we've done with limits is basically limit notation. So we have limit notation that says the limit as x approaches c of the function x, of the function f of x rather, is equal to L. So we've talked about in general, in a very broad sense, mostly talk about with end behavior and with asymptotes. But the real definition of limits is if f of x if f of x becomes arbitrarily close to a unique number L as x approaches c, then the limit of f of x as x approaches c is L. So L is a real number. C is a real number. F of x is a function. And if we're talking about c as x approaches c, c has to be an element of the domain of f. So if f of x was, say, square root of x, there's no way that c could be a negative number because it's not an element of the domain of f. So whenever you have a limit, you can only approach values within the domain of the function that you're working with. You cannot approach values outside of that. It's just impossible. It's never going to happen. It's never going to work. Now, notice how I said that c and L are real numbers. This actually goes against some of what we've done. We, for the most part, have been working with limits with respect to end behaviors, but really those aren't true limits. We just use this notation because it's something that is already established and it's easy to work with. Same thing with limits as we have asymptotes, as if we have asymptotes. But we're going to get into that a little bit later. So, to find actual limits, there are a few methods. One of the methods is with numerical analysis. So let's say we have limit as x approaches 2 of 3x minus 2. So first of all, that has to be a function inside. It is. It's a linear function. So we're looking for what that function's approaching as we get closer and closer to. So we can do numerical analysis. And one way to do that is with the table. So I'm just going to do x and f of x. And just going to put 2 here. So we're trying to find out what the function approaches as it gets closer and closer to. So we can take values that are getting closer and closer to. So like 1.999 and 1.9999. And approaching from the other side, 2.001, 2.001. So if we take this and we find out what these values are, I'm just going to use my calculator because we're setting up a table. And a lovely thing about our calculator is that, oops, I'm in polar mode. Let me just change it to function mode real quick. A lovely thing about our calculator is if we do 3x minus 2 in our y1, and I'm going to go in my table set and make it so we ask for the independent variable. And then go to my table. I don't want these values. I want new values. We can use this to find out how it's approaching. So if we did 1.99, 1.999, 1.999, you can, I accidentally punched in 3 nines and twice, doesn't matter. you can see what it's going towards. And if you try it from the other direction, you can see what it's going towards as well. So from below, as you get closer to 2 from the negative side, you're getting closer to 4. As you're getting closer to 2 from the positive side, you're getting closer to 4. I don't know if you can see that well. There we go. So there's a clear shot of the calculator. All right, so you can use your calculator to get a table that's getting closer and closer to 4 from either side. And that's what it is. Now, if you check, what is 3x minus 2 when x is equal to 2? It is 4. It's 6 minus 2, which is 4. All right, so sometimes it's going to work out nice like that, where if you just plug in your value, if you plug in c, you're going to get what your limit is. But that's not always going to be the case. Let's say we want the limit as x approaches 2 of 3x squared minus 8x plus 4 over x minus 2. Just a quick thing, you don't need parentheses around this, but it's helpful to put parentheses around your function when you're working with limits. It just helps you keep it organized. So this one, we definitely can't plug in 2 because it's just going to be 0. So we'll be dividing by 0 in the denominator. So we'd have to do the table again. So we're going to clear that out. 3x squared minus 8x plus 4 divided by x minus 2. Oops, that has to be in parentheses. There we go. So we have our function in y1, and we're approaching the same 2, so I can leave the same inputs that we had before. Don't want the graph. Want the table. So we can leave the same x values that we had before, 1.99 approaching 2, and 2.001 approaching 2. Oh, look, it's approaching the same thing. Even though we couldn't punch it in, even though we couldn't plug it in. But if we analyze this as a function, this rational function, that numerator factors to 3x minus 2, x minus 2. So the function is 3x minus 2, or x can't equal 2. So the graph would be the same as the last one, but it has a hole at 2. So the graph would be a line with a hole here. Graphically, a limit is what is happening as you get closer and closer to the value, what y value they're approaching, what function value they're approaching as the input values get closer. It doesn't need to be a point for there to be a limit. There doesn't need to actually be a point at that value in order for there to be a limit. In fact, you could have a piecewise situation where you have that and you have this point. Say this situation was mapped by f of x equals, I'm going to need more room than that. Sorry. F of x equals 1/2 x plus 2, but x can't equal, say, 4. And then it's 8 when x equals 4. So this could be our function. The limit, just going to change colors. The limit as x approaches 4 of f of x is not f of 4. F of 4 is 8. That's this point. The limit, what the function is approaching, what it's getting closer to, is actually this value here, which would be 1/2 times 4, which is 2, plus 2, which is 4. So if this was that function, that will be the limit as x approaches 4. The limit is not necessarily on the function. It is what the function is trending towards. So it doesn't have to be a part of the function. It's what the function trends towards. But functions don't always trend toward the same thing from the left and the right. Let's take the function f of x equals the absolute value of x over x. The graph of this well, for every positive x, it's going to be a positive over a positive. So it's going to be something over itself. So essentially, it's the line y equals 1 for every positive value. But for every negative value, it's going to be a positive over a negative. So something over its opposite. So it would be -1. And we have open circles here because it definitely can't be 0 because you can't divide by 0. Now, if we were to do, say, the limit as x approaches 3 of f of x, it would be, let's say 3 is about here. We'd be looking there how it's behaving here. And it's approaching the same value, it's approaching the same y value of 1. So that would be the limit over here. But if we were to look at the limit as x approaches 0 of f of x, well, from this side it's approaching 1, from that side it's approaching -1. So it's not approaching anything, it's approaching two things. There's not a set value. And our definition of a limit was the value of that it's becoming arbitrarily close to. So it's not two values that it's becoming arbitrarily close to, it's the value. So if it's not approaching a single value, this is what we call a limit that does not exist. So like in Mean Girls, the limit does not exist. That's how Lindsay Lohan's character Katie Heron won the Mathletes competition before going and crashing prom. But that's a completely different story for another time. So there is no limit at 0. But it's approaching something from the left side, and it's approaching something from the right side. We don't just have to have it approach from both sides. We do have right side limit and left side limits. But the notation is different. So this is talking about both sides. If we're talking about from just the left side, we're coming from negative infinity towards that value. So the notation for a left side limit, on your C, on the value that your x is approaching, you're going to have a superscript of a negative sign. It's still of f of x. This is not the limit as x approaches 0 of negative f of x. It's the limit as x approaches 0 from the negative side of f of x. That is a superscript on 0. It is not part of our function. And that value, it's -1. If we're approaching from the right side, which is coming from positive infinity, it's the limit as x approaches 0 from the positive side of f of x, which in this case is 1. So you can have positive and negative limits. You can have positive side limits and negative side limits. So from the positive side, it's a right side limit. From the negative side, it's a left side limit. And those limits need to be the same in order for you to have a general limit, which is talking about both sides. So the statement, the limit as x approaches c of f of x equals L if and only if, I don't know why that f was so weird, if and only if the limit as x approaches c from the left side is L, and the limit as x approaches c from the right side is L. So the only way for a limit to exist is if approaching from both sides, it's the same. All right? This brings us to our first tricky case. Let's say f of x was square root of x plus 1. So the graph of this is that. Now, negative 1 is part of our domain. But the limit as x approaches negative 1 even though it's part of our domain, you can't approach it from the left. So technically, this limit does not exist. You may have teachers in the future that say that that limit should actually be 0. I'm not one of those teachers. I believe that if there's no left-hand limit, there's no limit. There's no general limit. So this is what I'm expecting. I'm just warning you, you may have teachers that expect that. But I just want you to see that. I am going by this. All right? I will always be going by this. This exists if and only if those are both true. Now, there are a couple other ways in order to get a limit that doesn't exist. It doesn't have to be just that the limits, the left and right side limits, do not approach the same thing. Another way it can work is take f of x equals 1 over x minus 2 squared. The graph of this, numerator has a lower degree than the denominator. So we have a horizontal asymptote at 0. We also have a vertical asymptote at 2. And the curve, well, we would have a y-intercept at 1/2, 0, 1/2, I should say. So we would have a piece up there. And then if we did sign analysis and plugged in something greater than 2, say 3, 3 minus 2 is 1, 1 squared is 1, so we'd have a point at 3, 1. So it would behave like that. Now, if we were to talk about the limits, the limit as x approaches 2 from the left of f of x, and the limit as x approaches 2 from the right of f of x. Technically, technically, our limit does not exist. Technically, these limits do not exist. And that goes back to our first definition of limits. I think that's my first slide. Oh, kind of scraped off some of it. But if you look, oh look, the limit equals a real number. Are both sides approaching a real number? Last I checked, infinity is not a real number. But to simplify our work with end behavior and behavior at asymptotes, instead of developing an entirely new system, technically these are not limits, but instead of developing an entirely new system to express this, we accept that. These are not true limits, but this notation helps us to understand that. So we just keep in the back of our mind that these are not true limits because they are not real numbers. But if the function is approaching infinity, we can mark that. But the limit does not exist. But since these approach the same thing, we can say this just for the sake of simplicity, just so we don't have something new to just discuss this very, very specific case. This is a very specific case that comes up frequently when we're talking about behavior at an asymptote. And since we already have limit notation, we've just kind of co-opted it. It's just like how you've the same word that means different things. All right. So that's basically this. These are not true limits. In actuality, the limit does not exist, but we still use that. I know it's a little confusing. Sorry, guys. And there's one more instance where the limit does not exist. And this is a very rare case. We're not going to come up with it pretty much ever in this class except this example. And this example is just to show you what's happening, to show you this possibility. This comes up in calculus more, especially higher order calculus. So like calculus 2 and 3, multivariable calculus, things like that. Also comes up in physics more. But this function, sine of 1 over x, all right. Well, it's a sine function, so it's bounded between 1 and -1. Now, this curve has a restriction on x. X cannot equal 0 because you can't divide by 0. So there's going to be a hole at this axis. What the rest of the curve looks like. It behaves kind of like a sine on the outskirts. But since we're dividing by x, instead of 1 times x, it's 1 divided by x, we're actually changing the period not on a linear scale like we would if it was just sine of 2x. We're changing it on an exponential scale. So the period is actually going, as we get further out, the period gets wider, but as we get closer in, it's a very, very infinitely narrow period. So it's going, and that's even narrower. And then it's even narrower. And then it's just so narrow. It basically is like a solid block inside here. And it gets wider as you go out again. It's just constantly oscillating between 1 and -1. Since it's oscillating between 1 and negative 1, if you try and take the limit as x approaches 0 of this function, for every point where you're at 1 on the right side, there is actually a point closer to 0 where you're at negative 1. And then for every point you're at negative 1 on the right side, there's actually one closer to 0 where you're at 1. So you're constantly bouncing back and forth, and you can find a number closer to 0 where you would be at the opposite value. So since you're neither approaching 1 or negative 1, you don't just take the average of those two. So it's not like you can't say, oh, well, it's approaching 0. It's not. It's not approaching anything because you're constantly switching back and forth between what it approaches. So that's when it does not exist. So a limit doesn't exist if it's bouncing between two oscillating values or oscillating between two values. A limit does not exist if it's approaching infinity or negative infinity, but we do still use limit notation just for simplification reasons. And a limit does not exist if the left and right side do not approach the same value. All right, so that's our introduction to limits. We'll be spending some more time with this later. Okay, bye.